Greetings. My talk is about extreme events and about the classes of distribution that deliver extreme events and how we should deal with them. The idea that there are two very separate domains, easy to identify. Ebola, for example, can deliver extreme events. Other diseases, say toothache or stomach ulcer or something, cannot deliver extreme events. So they have different properties. We're going to explore these properties. We're going to say where most of what you learn in statistics doesn't work, okay, in what I call extreme stand, that domain, and we'll study the different conditions under which they occur. What else I'll be talking about? I'll be talking about also mistakes made in psychology literature concerning tail events, why some of the decisions we make that appear to be very irrational, in fact, are extremely irrational. I'm honored to be in Cambridge, which is the house of that, of course, Cambridge is Cambridge, and had Wittgenstein and all that. There's also Martin Rees, who has a center on existential risk. And we're going to discuss the properties of events that can lead to these existential risk and show why your grandmother knows about them, but not your psychology professor. So try to avoid economists, psychology professors, and you live longer. Thank you.
Good evening. Good evening and welcome to the second of the 2017 Darwin College lectures on the theme of extremes. Last week we heard about extremes in weather and climate. In the cold, harsh days of the Younger Dryas period, some 11,500 years ago, musk oxen, reindeer, and woolly rhinos searched for lichen. Dryas flowers bloomed over the permafrost in the muskeg. Where? Here, East Anglia. Advance maybe 20 years. The air is filled with buzzing insects, birds, flowers of spring. The modern Holocene climate suddenly arrived. A very sudden change. Advance again to about 8,000 years ago. You could walk dry-shod to Paris. Possibly the king of Doggerland sent warriors here to hunt now extinct wild cattle. Then there was a huge landslide off the Norwegian coast, potentially triggered by a giant earthquake. That sent a 20-meter or so tsunami across Shetland. Doggerland vanished, completely submerged, and the catastrophic flood scoured the English Channel. Sudden catastrophic events, though, aren't just confined to the natural world. Events, dear boy, events. That was Harold Macmillan. Less elegant was Donald Rumsfeld's stuff happens. But he did better, of course, with known knowns, known unknowns, and easily trumping Macmillan, unknown unknowns. So unknown unknowns, to go to the natural world, you think of a fat, happy turkey in the early winter, a cheerful mayfly, or even a mating male praying mantis. None of them know what's before them. Extremely unusual events occur. How should Mediocristan prepare for the unexpected capture of their castle by the leader of Extremistan? Now, mathematicians like singularities. They're interesting. But to the leaders of Meritocristan, they're unknown unknowns, potentially terrifying blackbirds of the Black Night. The Roman satirist Juvenal wrote in Latin, "Rare bird on the earth, as rare as a black swan." but he didn't know that black swans existed. They're Australian. So can robustness be built against the unexpected? Here from the US to talk on, as you see, the logic and statistics of extremes is the expert, Professor Nassim Taleb, a statistician, financier, risk expert, and writer. He first used black swan terminology in his highly acclaimed first book, 2001, Fooled by Randomness. The Inserto, that's a 4-volume book, a book set, includes Anti-Fragile, How to Live in a Black Swan System. That came out 6 weeks ago or so in November, I gather. But now there's another book available online, the title of which I've just been told and I've forgotten. I'm sure Nicholas can tell you about this. Please welcome Nicholas Taleb.
Thank you very much. Thank you. Okay. There's no game tonight or something? Okay. So basically, I'm going to summarize the talk in 5 minutes, and then the rest is details. You can leave right after, at minute 6 of the talk. Okay. With a few heuristics, few tricks, and then the rest, of course, becomes what we call academic in the bad sense of the word, not the good sense of the word. Okay. So the Inserto project, for some reason, I was a trader, and then I stopped trading. And when you stop trading, you got to occupy yourself. You want to occupy your days, your afternoon. I was incompetent at all, at bridge, chess, no attention span. Being a trader is natural, and absolutely incapable of playing tennis. You lose, start daydreaming. So I decided to start doing research. So that was, so I went from trading 21 years, focusing on tail events, to try to formalize it. And do research because you can do it on your own. You don't have, someone getting impatient because you fall asleep while playing chess or that kind of stuff, okay? So the project is the Inserto, and it's, of course, 4 volumes, but as we mentioned, but I tried to connect different disciplines that are not connected to one another, mostly related to tail probabilities and extremes. Even within mathematics, some parts don't connect. Decision theory doesn't connect to extremes. Statistics, a lot of branches don't connect to extremes. So there are 5 disciplines. In black is what I call the real world Fat Tonyism. There's a character in the Inserto called Fat Tony, who's, as his name indicates, is street smart and likes food, okay, knows good restaurants. And so it's pretty much, it's not empirical, it is not theoretical, it's different. It's the real world, it's contact with reality via decision making and survival. There is legal theory, small here for contract theory. I see options as contract theory. So I tried to connect them, and this is available on the web, okay? That's the Inserto project. So volume 5 will be around the symmetry, where you're an option trader, you understand asymmetries. I own an option, you short an option, okay? I have unlimited upside, you have unlimited downside. But I have limited downside, you see, and you have limited upside. So this is pure legal theory, except mathematized. So try to connect these, and the next one is skin in the game, the next volume. And they're all the same story, how to live in a world that has a structure of uncertainty that's too complicated for us, and certainly too complicated for statistician, mathematician, philosophers. So that's the Inserto project. Okay, it keeps going, keep adding volumes, and if I ever become better at chess or bridge, maybe I'll stop, okay? And there's some technical papers. Now let me explain the notion of fat tails, how it relates to extremes, with that notion, that distinction between mediocristan and extremistan, or the 2 domains that are very separate. Randomly select 2 people from the UK and assume that you lucked out, you got a tail event, a total of 4.1 meters, 410 centimeters. What's the most likely combination you're going to get? 4 meters and 10 centimeters? No, what's the most likely combination? Conditional on having 4.1 centimeters as a total for two people. The probability of exceeding 3 sigmas is something like 1.35%. The probability of exceeding 6 sigmas, which is twice as much, is of the order of 10 to the minus 10. And so the probability of having 2 times an event of 3 sigma is something of the order of 10 to the minus 6. It's considerably higher than the probability of having 1 times 6 sigma. So 2 3 sigma events, as unlikely as it is, happens 1 in a million approximately, is vastly more likely than having 1 times 6 sigma, okay? And that's a definition of that class of distribution that is not fat-tailed. And we're going to see the logic. And the graph here shows you, okay, as you extend the sigmas, as we're looking at the ratio of 2 events, say of 3 versus divided by 1 event of 6, 2 events of 5 divided by 1 event of 10, and look. So the more you go into the tail, the more you realize that a large deviation can only occur via a combination of a lot of intermediate deviations. You see? That's the logic of what we call mediocre stand. Let's go further here. So this will explain the difference, because let us assume now that you randomly select 2 people, and their combined wealth is $36 million. I don't know the exchange rate today, but assume, okay. What's the most likely combination? 18 million and 18 million? No. What's the most likely combination? Approximately, say $1,000 and 36 million minus 1,000, right? Okay, so here, so you see the difference between the 2 domains is very crisp. Okay, so now we have pretty much, now the mass is to the right, ignore it, unless you're a mathematician, okay? This is the legal disclaimer here on the right, okay? So you don't get annoyed with what's on the left, which is actually sufficient for most people, including mathematicians. The catastrophe principle, for a class of sub-exponential distribution, ruin is more likely to come from a single extreme event than a series of bad episodes. That's it. So in the domain, the second domain, like wealth, if I say that, if someone tells you the net worth of this room is £1 billion, okay, you know that can't come from each person here having a net worth of 15 million pounds. It's much more likely to come from, it's a tail event from someone with a, with a net worth of £1 billion who just happened to visit, okay? So, and if you follow this logic, now we follow this logically, okay? Simple, logically. It's going to take us quite far, okay? Let's start with classical risk theory, where this was born. Kramer, 1903, 1930, actually Lundberg, and then Kramer formalized it. That basically, insurance can only work in mediocre stand. You'll never have today, except for someone who worked for Lloyd's of London and didn't understand the problem. And Lloyd's of London, I'm talking about, was a name for Lloyd's in the 60s, 70s, and 80s. You never have an insurance contract that's uncapped for that reason. So catastrophe, so this was understood long time ago, and of course people forget about it. So now let's define fat tails formally, okay, or more formally with more intuitively for all of us, okay? Fat tail distribution are one in which extreme events, the ones away from the center of the distribution, play a very large role. That's it. It is not as when people start talking about black swans, they say black swans are more frequent. No, they're not more frequent. They're more consequential. The fattest tail distribution is one in which you would have one very large extreme deviation, you see, not many departures from the norm. And if I take a distribution like the Gaussian and start fattening it, you notice that effectively the number of the departures away from one standard deviation drop. So let's take a Gaussian. What's the probability of a Gaussian staying between -1 and +1 sigma? 68%. If I fatten the tails, what happened to that number? In other words, we have 15% probability exceeding, 15.6% probability exceeding 1 sigma, or 15% to be below 1 sigma, okay? What happens if I fatten the tails? No, it goes up. The probability of staying in the middle goes up. If you take financial markets, it's somewhere between 75 and 95%, between -1 and +1 sigma. Incidentally, sigma has no meaning with fat tails. But you stay, because you have fewer departures, you have higher peaks. And this is what happens. You have higher peaks when you fatten the tails. Higher peaks, higher incidence of very large deviation, and smaller shoulders, okay? For net departures away from 1 sigma to drop in frequency. So, I mean, it was painful for me to spend 10 years reading about my book, The Black Swan, by saying Taleb is saying they're more frequent. No, they're not more frequent, okay? So it's painful. So let me continue. This is in higher dimension. Which one is fat tail, the left or the right? The right. As you see, more events in the middle. But those that depart from the middle go further. So what happens when I fatten higher dimension? Okay, now, taxonomy. They're effectively, I've cheated so far, I've lied. You know, that's what you do when you want to be pedagogical. But now let's be a little more so nobody here leaves with the wrong impression. There are 3 types of fat tails. Level 1, entry-level fat tails, we call it, is anything with fatter tail than Gaussian, okay? You take a distribution, and it's a very simple one. You count how many observations are between -1 and +1 sigma. If it's more than a Gaussian, it's fatter tail, okay? Level 1. Another one is there's a measure for fat tailness in the Gaussian world, and what is it? 4th moment, kurtosis, okay? Kurtosis higher than 3, okay? That's a measure of fat tails. These fat tails are not really fat tails because they don't have these big impacts. Level 2, sub-exponential class. Level 3, something vastly worse. So now, as they say actually it's actually apocryphal, he who said it, and it's not true. They say Eskimos have several hundred words for snow. All right, it's not quite true. But we have a lot of words for fat tails, as you can see, all right? Because there are a lot of varieties of fat tails, okay? So what we have is a degenerate distribution, nothing moves, and then Bernoulli, and then the Gaussian. When you stop here, there are 2 Gaussians. There are a natural Gaussian and the Gaussians that you reach by adding random walks. They're completely different animals in the sense that one can actually deliver infinity, the other cannot, okay? Except asymptotically, which, right? And then the sub-exponential class, as you see in yellow, these have all moments. But the sub-exponential class includes something called the log normal, which is the weirdest thing you can imagine on the face of the earth. Because it acts in this class, but sometimes it cheats and goes up here. We're going to see how. And then once you leave the yellow part, as you see, law of large numbers works in this, sort of. Then you have convergence problems. So now here we have what we call power laws, and we're going to see in details what they are, Pareto and Pareto laws, second class. And then there's one called supercubic. Oh, sorry, no. Supercubic, Levy stable. So this one has no variance from here, okay? No variance. This one has no mean. And as you see here, there's something called forget about it in Brooklyn. If you see something in that category, you just go home. You see it, you go. You just don't talk about it, you don't discuss it. Yeah, I know, like the kind of thing, we don't know what it is, you have never heard of it, you go home, because you don't want to talk about it, all right? Because if it doesn't have a mean, it's very hard, okay? And then here, there is no standard deviation, but there is something called mean deviation, all right, mean absolute deviation. And here, the Cramer condition apply till here, which means that you can do insurance up till here. So there are a lot of, this is called compact support, this is called Cramer condition, this is called L1, and this is called forget about it, all right? So these are the way I view fat tails, but some people view them differently. With an exception for, I say, the non-practical mathematical classification, because I put the log normal, which is here, in practice, here. And we're gonna see why. So it is, as they say, complicated, but we can make it simple, right? Slightly simpler. Now, reasoning error is not changing the color of the dress. The traditional approach by statistician has been, oh yeah, we know about fat tails. So for them, the illusion is that it's fat tails, oh, it's different, we have all these methods, we just assume a different distribution. No, 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 it's not how it works. You fall into logical inconsistencies. Because once you switch from the zone here, on which statistics was made up to here, okay, law of large numbers weak. You stop here, no, even below, you stop here. Once you get out of here, linear regression, haha, doesn't work. A lot of things you think work don't work no more, okay? So let me give you a slide that says everything, and then we're gonna go into detail with more anecdotes. The law of large numbers, when it works too slowly in the real world, period. Okay, we're gonna see actually it's more shocking than you think. Point two, the mean, the distribution that you're gonna observe will not correspond to the sample mean will not correspond to the true mean. So you're gonna have a problem measuring a mean that's not the real mean. This is what think people in finance, they still didn't get it, okay? They still didn't get it. For some reason, people in finance, or maybe they don't want to understand it, that the mean return is not the true return, and we're going to see how. Standard deviation and variance, they don't work under fat tails. They already, don't work under thin tails, but let's say on the fat tails, you got a problem, okay? Because it's not a measure that works, mean absolute deviation may work. Beta Sharpe ratio, you've heard of these things, they don't work, okay? Robust statistics is not robust, okay? So it's like pretty much like anything. They say Scientific American is unscientific and stuff like that whenever you have. So robust statistics is not robust, okay? Maximum likelihood methods work. That's good news for parameters of distribution. And then we can have plug-in estimators. The gap, and then the philosophical point, the gap between this confirmatory and confirmatory empiricism is wider than common statistic. In other words, the difference between absence of evidence and evidence of absence becomes bigger and bigger and bigger. It's very weak with thin tails, it's very big, large, it's very weak with thin tails, it's very acute with fat tails. Method of moment that just gave another Nobel to one of these guys, they don't work because higher moments are uninformative, okay? And we're gonna see how. And then there's no such thing as typical large deviation. And finally, the Gini coefficient ceases to be additive. The Gini coefficient actually becomes superadditive. There's a problem with Gini. If you compute Gini, you have the illusion of concentration of wealth, when in fact it's just like what I call the Pikettism. Pikettism is you write 500 pages to hide the fact that your measure doesn't work, okay? So Pinkerism is when you write 800 pages, right? So there's the, okay, so now also we have an expert problem because visibly this fellow didn't quite get the notion of fat tails and stability. So let me start now with the easier. You see there are going to be some slides that are boring with words or equation, and think of being in Spain, all right? And then the rest is, they're more palatable, okay? So there is a severe error in reasoning, and that you often hear by people giving you empirical data and telling you, for example, that we're idiots to worry about Ebola that killed 2 Americans when more people slept with Kim Kardashian that year, okay? Okay, so for example, And that was effectively the number they said, that more people slept with Kim Kardashian in 2014 when we were worried about Ebola than died of Ebola, for example, right? So now, and then sometimes you see numbers like these, and this is the kind of thing that if you read something called the New York Times, and you still read that nonsense, this kind of stuff you read in it, which is factually right, but bogus, okay? Well, and the kind of thing that teach in psychology department, that so many Americans die from eating too many hamburgers, smoking too much alcohol. Now let's think about it in terms of tails. If I tell you, or let's say Steven Pinker gave the number that 3,000 Americans die in their bathtub every year. Okay, 3,000 people, whereas 2 have died of Ebola. Now let's play a thought experiment. If you read in the papers, if you go, to Mars and come back, and then read on, on Google News that 2 billion people have died, what's more likely to have killed them? Diabetes, obesity, falling in their bathtub, sleeping with Kim Kardashian, or Ebola? Ebola. Okay, there we go. So you cannot compare. Rule number 1, thou shalt not compare a multiplicative, fat-tailed process in extremistan in the sub-exponential class to a thin-tailed process that has what we call Chernoff bounds, okay? And that is totally from mediocristan, simply because of the catastrophe principle, okay? And then we know, for example, that it's very cheap to protect yourself from Ebola. You see, the probability that people dying from smoking, okay, is multiplied by 10 next year is 1 to the 10 minus 30. The probability that the rate of people who died from Ebola triples is vastly higher, you see? So you cannot compare processes. Thin tail to fat tails are not comparable. So this is not empiricism, this is called naive empiricism. It's actually worse, okay? So you cannot compare 2 processes like these by saying we worry too much about Ebola. In fact, we worry too much about diabetes and too little about Ebola. So that's one error of reasoning that comes from not understanding fat tails. Now, let me show you the law of large numbers. Everything you learn in statistics is based on a well-functioning of a law of large numbers, no? All right, so in other words, it tells you that as you add observation, the mean that you observe would be very stable, no? And the rate is square root of 2, or square root of n, number of observations. You agree? All right. This is what you have on the left. Now, on the right, for a fat-tailed process, the mean exists, but it takes much longer to observe it. Much longer. You need many more observations, okay? I'm not going to go very far and cite the most commonly known statistical phenomenon. It's called Pareto's 80-20, on which later, technically, but now let's mention it. You've heard of Pareto 80-20, okay? 20% of Italian owned 80% of land, 80% of Italian owned 20% of remaining land, okay? 20% of students, you get the idea, all right? Okay? 80% of 20% of the activity that happened, after lecture. You get the idea, all right? So that's the Pareto 80-20. So let me ask you, for some reason people in textbooks take 30 observations for the Gaussian to say how much you shrank the mean, okay? So I have n of 30, my sample. Your variance drops. How much do I need for Pareto 80-20 to bring down my variance by the same amount? Twice as much? 3 times? Someone help me? Sorry? How much? Twice? Okay, let's keep going. He said twice. You need twice. In other words, you need twice as much data to bring down your mean, to have certainty about stability of the mean, to shrink your mean. Let's continue.
I did 100.
How much?
100.
Keep going.
1,000.
Keep going.
10,000.
Who said what?
10,000.
Let's keep going. Who's the highest so far? This is the table here. If the mean exists, this is forget about it. The Pareto 80-20, 10 to the 11. 10 to the 11. In other words, it's a lot of data to have the same error with the Pareto 80-20. Okay? So, and this is trivial to compute, but for some reason people don't compute it. So you cannot make claims on sample mean, on the stability of the sample mean on the basis of data with a fat tail distribution. There are other ways to do so, but not from observation sample mean. Okay? So, now let me do some epistemology, some philosophy, because I know that this is a big place for it. And the Wittgensteins and Schmidtgens, a lot of things here, and Russell. And then we go back to a little more destabilization of people who have studied statistics and economics, okay? So let's do some epistemology here, all right? And I'm proud of it because it's the first paper I ever wrote. It took 5 years to write it. It's longer than writing a book. And let's say I observe a degenerate distribution, okay? In other words, there's no randomness. All observations come at 2, okay? Can I rule out that the distribution is random? I cannot logically rule out. We've known that from people in the UK claim Hume, but we've known that from Sextus Empiricus, okay? Via like another 75 people who asserted that, okay? That's a black swan problem, okay? You cannot rule out that you cannot say there are no black swans. Likewise, if I see a distribution that has no randomness, I cannot say it is not random. But let's say now I add one observation and I notice that effectively it is random because it's not all degenerate at 2. It has another observation. Can I rule out degeneracy? Yes, I can say it is not non-random. You agree? Like I've seen a black swan, I say the statement that there are no black swan is wrong. So I have information. That's the whole idea of Western science based on negative empiricism. We can rule out some things, and here we can rule out that this is degenerate. In other words, deterministic. Sorry, I don't know what words you use for degenerate. That is politically correct, but that's the one still used by mathematicians, all right? So degenerate distribution is one that has no randomness in it, okay? And no variation, okay? So you have an additional variation. Okay, so this distribution can hide as this, but this one cannot hide as that, okay? This gives us a very easy way to deal with randomness. Because if I see a 20 sigma event, I can rule out that it's entailed. If I see no large deviation, I cannot rule out that it's not fat-tailed, unless I understand the process very well. This is how you can rank distribution. So here, I have the tableau that I showed you before, and we can start seeing deviation and ruling out from the bottom. You see? And the true distribution rule out progressively all the way to go up to 1. And those are based on how they can deliver tail events. You see, so this is a technique. I don't have a lot of time. This is worth flying in and spending time bickering with philosophers and logicians about it. But so this is ranking distribution becomes very simple because someone tells you it's a 10 sigma event. It's much more likely that you have the wrong distribution than having a 10 sigma event, okay? And likewise, fat-tailed distribution, as we saw, don't deliver a lot of deviations often. Once in a while, you get a big deviation. So we can already rule out what is not mediocre stand. Like we can rule out in finance and economics that we are not. We can rule out mediocre stand. We are not in mediocre stand. I can say this distribution is fat-tailed by elimination. I cannot certify that it's thin-tailed. That's, again, to repeat it, the black swan problem. Let's continue now. Pareto in class. Now I have 2 pictures of Pareto. One when he was young, before he discovered the Pareto distribution, which is a power law, and one after. And you see what happened to him after discovering the distribution. In the meanwhile, he had a Russian wife whom he met in Venice, who left him, okay, with his 22 cats, all right? So you can understand, and something common here to have a Russian wife, but except that in the case of Pareto, from what I hear, compared to your local resident who had a Russian canes, he apparently slept with her. So she still left him. That's probably why she left him, whereas with canes, you know, all right. So that's what, so now we know about Pareto, okay? So what is important about Pareto? This is the math. But let me give you the intuition, okay? Let's say that we have a Pareto distribution. Probability of richer than 1 million, 1 in pounds, or whatever you want, lira, the Italian, whatever you want, okay? 1 in 62 and a half. Do you see a logic here? Richer than 32 million, 1 in how many? Sorry? You multiply. So the ratio of people with over 50 million over 25 million is similar to the ratio of 500 million over 250 million. You see? So this distribution has no characteristic scale. It makes it very easy to understand. The ratio of people who are 500 pounds over 250 pounds is not the same as 1,000 pounds over 500 pounds. You see, in the thin tail. For fat tail, that class of fat tail, you know, we have 3 classes of fat tail. That's the one to the extreme right, sort of the Le Pen of fat tails. So that has this characteristic that makes it very easy to understand. Okay, for large deviation, it may not start at 1 million for large deviation. I'm simplifying. Another one, how many are richer than 32 million here? 2,000, no? We understand you can do it on a napkin. Now, what do these two have that is problematic for statistician? Sorry? This distribution has no mean, and this distribution has no standard deviation. We still understand it, no? Well, get used to it. You're going to have to ditch standard deviation, and you still understand what's going on. And for extreme events, you have to ditch the notion of mean, because it becomes mean. You're only interested in the extreme event, okay? So forget the mean, or you can't compress things in a fortune cookie style statistical textbook. You can't, all right? So ditch the statistical textbook. Forget statistics and relearn how to deal with these things, okay? So, and now I have bad news for people in economics, except for those at Cambridge, because of course they're one class apart. But I'm saying that people in economics in the US have a problem with the following. And this is what really made me bitter. People wonder why I have this allergy to the economics establishment. And it came from this. When and let me give you the point. We said that in the Gaussian world, or in the thin-tailed world, a measure of fat-tailedness is what? The fourth moment, no? So I took, that was in 2009. I took 55 years of data and looked at how much of the kurtosis came from the largest observation. For the S&P 500, it was about 80%. You see? What does it tell you? It tells you we don't know anything about kurtosis. If you don't know anything about the fourth moment, you know nothing about the stability of second moment. It means you're not in a class of distribution that allow you to work with variance, even if it exists. That's finance. So here I have financial data, silver future. In 46 years, the 94% of the kurtosis come from one observation, S&P 500. I mean, you can replicate it, take the top 3, because since 2009, we've had some tail events. So look at this. This is not consistent. If I take, this is not at all consistent with anything you can use standard statistical methods with. Okay, that's not. Because something called Garch doesn't work, because you're dealing with squares. The variance of the squares, sort of as the fourth moment, doesn't work. Okay, it means we don't know the variance. But you can work very easily with Pareto distributions, which gives you less information, but nevertheless, It's more rigorous. You cannot invent information. So this I discovered. So basically, based on this, I kept writing. I wrote on the black swan. I revised it on the black swan. I said, anytime you hear standard, you read a paper, you see if they use any moment, you take it, you tear it, there's a shredder, you put it in a shredder so it goes back to nature, and then put it in a recycle bin. The recycling, then they make paper with it, whatever it is. You get the idea, all right? But don't continue reading it if it has standard, unless it is capped. If it's an open variable and some classes of macroeconomic variables, you can't use this with. This is logical. Now, what? In 2000 whatever, they got a guy who got the other called Lars something, and he got the method of moments. He got the medal, the Swedish medal. So I wonder. So I told myself, you know what? I want to live in my own world. Because it doesn't make any logical sense. You don't need a lot. You need just this slide to debunk all of these methods. You don't need a lot of text for that. All right? You can wrap it up in 1,000 pages of equations. Okay? So let's talk about something else that goes out the window. So here, what goes out the window is a lot of econometrics that deals with squares. Okay? Anything that has squares in it. Squares or higher powers, just take it, and again, because it's useless, all right? And this explains why they can't forecast what's going on, because you use the wrong methods, okay? In sample, it will work, but out of sample, it won't work. If I say variance is infinite, you're not going to observe anything infinite in sample. But it means as you keep having data, it will get different values all the time, you see? So that's what it means. Even if the mean is finite, if it takes so much to know about it, you can't deal with it, okay? It's not something workable. Anyway, so this is PCA, Principal Component Analysis. Principal Component Analysis works beautifully with thin tails, dimension reduction for big data. But the problem is, you know that there is noise. If I don't have enough data, I have an illusion of a structure, but as I increase my data, my n variables, it becomes flat. And if this is data that has absolutely no structure. In other words, in expectation, you have a zero correlation on that matrix, okay? But for those familiar with the random matrix theory, Marchenko-Pasteur, you have some kind of errors on observation, okay, that makes you think there's a higher correlation, and that washes out as you increase n. So to summarize, for those not into PCA's principal component analysis, as I have spurious correlation, I get more data here, but then that washes out as I increase the sample size, and non-spurious stays. For fat tails, look what I got. Okay? And it doesn't wash out when I add data. You need to add a lot more data for it to wash out. So that's dimension reduction doesn't work well with fat tails. Actually, it doesn't work with fat tails. Okay? There are other techniques on that later. Now, this is simple because pretty much everything I've been writing about in the black swan is that there are two types of distribution. If the distribution it has one tail, you know, you're fat-tailed, you can be fat-tailed one tail or fat-tailed two tails, no? And if you're fat-tailed one tail, you're fat-tailed one tail left tail and fat-tailed one right tail, okay? So if you're fat-tailed and you look at the sample mean, what are you going to observe here? You're going to observe fewer tail events, do you agree? Like if we, the common mistake is to think, all right, that you can derive the mean, okay, in the presence of one-tailed distribution. But you have unseen rare events here, and with time these will fill in, but by definition they're low probability event. They won't come in your data easily. The trick is you estimate the distribution and then derive the mean. This is called, we call it plug-in estimator, not observing the sample mean. Sample mean will be biased down if it's like this and biased up like that, you see? So this is why when you take the financial returns, outside of crisis, the banks seem to be making a lot of money. And then every once in a while, they lose back everything more, you know, drain the taxpayer and elect a new government. You get the idea, right? So this is, so what happens, so there is this bias. So the way we handle it, here, it's a true mean versus realized mean. Is that, and there is a way to compute the true, once you can figure out the distribution, you can do it. Of course, it's not perfect, but it works a lot better than observing the mean. And this is, I don't know if you remember, if you know, you've heard of a fellow called Pinker. I have a particular, had a war with Pinker, but we published he wrote a book saying violence has dropped, looking at the mean. Visibly, the mean is very unstable. We applied extreme value theory to derive what would the real mean be. And we discovered the following, that the true mean of violence is 3 times sample mean. But he told them, no, there's evidence it has dropped. We're telling them, listen, in science, it's not journalism. In journalism, we have fact-checking. You see how many people died last year. But in science, you need to know if it's statistically significant. The statistical mean is not the same as sample mean. But in thin tail, they're almost the same all the time, so people don't know that problem. When you move to fat tail, you realize, you see, that for a fat tail distribution, the Pareto 80-20, for example, I don't have the number in my head, but it should be maybe 96% of observation are below the mean. 98% maybe of observation are below the mean, okay? So you realize there is a bias in the mean. But once you notice the Pareto 80-20 from fitting the distribution according to maximum likelihood method, something technical, I don't want to be technical now, okay? There's enough technical on the site and in papers and in forthcoming book, that you'll figure out that we should ignore sample mean for these things. But people do it, and they call it science. It's not science. It's journalism, you see? Science is not being fooled by the anecdote. It's separating, you know, that's the problem, okay? So people understand it very well when you say that in Microbe Égale in Voltaire, a fellow came in, saw that a whale on the earth, and said, you know, who would have said in modern terms, there's statistical evidence that all the inhabitants of the earth are whales, okay? From seeing a sample whale of 1. But he had evidence in a journalistic sense, but not in a scientific sense. Science is about saying my data is not anecdote, my N is large enough, and that it replicates outside, it has universality outside the sample set. And then what can happen to crime next year, or did violence drop, or is it noise, okay? So, now I'll finish with something simpler. I have another, 20 minutes left? I lost track of time. 20 minutes, okay. So we're going to talk about path dependence and time probability, okay? So I spoke about fat tails, scare you with fat tails, but let me tell you, they're not that scary. They're actually, if you don't know statistics, you understand them, your grandmother does. Your grandmother knows about fat tails, that's how they think. Why? Because we've been on this planet as humans for, I don't know how you count, but for a long time, right? I don't know if it's 5,000, I think, if someone's religious, or 6,000 enough, or define the species the last 200 million years, 200,000 years, whatever you want, okay? We figured out how to survive, okay, by making decisions based on some statistical properties, right? And then you have a bunch of people who say, we're irrational. Let's see how they're not irrational. Because once you do a little bit of science, you come up with mistakes. When you do more science, you may realize your grandmother has a point. So let's see how. Okay, we all heard about path dependence, and we should summarize that if I iron my shirts and then wash them, I got vastly different results from if I wash my shirt and iron them. You agree? Okay, so that's path dependence standard. And so this is a point, I know, as a physicist, Murray Gell-Mann and Peters, okay? Actually, this point was in my book, but let's put it this way, these guys discovered it and made the aggressive point that I didn't dare make in my point, that everybody made that mistake since the beginning of decision theory, including every textbook except for Kelly and Edward Thorpe, okay? And they show the mistake of ergodicity. Let's explain it. Let's say that what we call ensemble probability is 100 of us today, we select randomly, and then we have a group, we go to the casino. Is there a casino in the UK? Yes, in London. No? All right. So we go to the casino, 100 of us gamble, all right? Number 28 is ruined, okay? Okay, not you, no, it's number 28, so you don't feel. One of us goes ruined. What happened to number 29? He's not affected, no? So we can compute the return of the casino using the law of large numbers by taking the return of these 100 people who gambled over 10 hours. You agree? And then say, okay, this is our estimate, and then we do it 2-3 times, and we get a good estimate of what the edge of the casino is. You agree? All right, that's called ensemble probability, and this is how people think. Unfortunately, they try to apply this ensemble probability to you. It doesn't work, because if one of us goes to the casino and on day number 28 is ruined, guess what? There's no number 29. Okay? So if there is an absorbing barrier, if there's a probability, and I'm glad I'm talking about this because Mr. Rees from Martin Rees, the name, has a center here and this is very important venture. I don't know the details of what they do, but it's the most important thing to worry about survival for the following reason, because you can't use these probabilities of survival, because once you die, there's no more, okay? Now, who's aware of this? Every speculator. Because the techniques we use are based on gambler's ruin, and people in insurance knew that. This is why Kramer banned insurance outside what he called the Kramer condition, not finance, where they say these puts are expensive. They don't understand, first of all, the alpha of the market. This is the alpha return of the market. This is your return. You're not going to get the return on the market because you don't have infinite pockets, okay? And it's only under strict condition that you can get the return on the market, assuming they're right about the future returns on the market, okay? So this becomes an acute point that the only way you could use it is log, the equivalent of Kelly criterion using logs, because logs make it ergodic. This is called non-ergodicity, okay, where time probability and ensemble probability are not the same. Conflation of the two. Now let's see how we can work with these, and let me explain at the level of the individual how we can remedy it and what is wrong with the literature. If you visibly incur a small risk of ruin, it will go to 1. It's not a big deal. You can take that risk. But you can take that risk of ruin visibly. You know, if you ride a motorcycle, you have a small risk of ruin, but if you ride the motorcycle a lot, it's going to reduce the life expectancy, no? So the way to measure it is the reduction of life expectancy of the unit, assuming repeated exposure, okay, at a certain intensity, okay? Or frequency, whatever you want, okay? So if you're doing this, there's a guy who just died, I think I saw it on Twitter, all right? Today, okay? If you do this for a living, no ride is going to really reduce your life expectancy, but cumulatively reduce your life expectancy, okay? Now, this seems trivial to your grandmother, but I don't know if you heard something called behavioral finance, okay? They make you take the thing and they say he overestimates the risk. They forget that, hey, you know what, tomorrow you're not going to go home. Plus risks accumulate. If you sleep with people who have AIDS, join the mafia, ride a motorcycle, smoke, all right? Engage in walking on tight ropes like this fellow, all right? All these risks add up. So when we look at risk of humanity, you have to add up all those tail risks. And who understand Warren Buffett? Even Goldman Sachs, the evil firm Goldman Sachs, they say we're in the business of taking tail risk. We don't want small, we want zero. And there's a difference between small and zero. Because a small difference between small and zero means survival of our firm over 20 years. They get it. It's not in the literature. But you practice it every day. You take planes, no? Many of you take planes, all right? Planes don't reduce your life expectancy. Why? Because if we were to use the psychologists say, oh, he overestimated the risk, no pilot would be alive today. You see? So the way to look at risk is you take a unit, you take how much life expectancy you want it to have, and see how much that risk reduces the life expectancy via repeated exposure. That's the way to do it. Not in literature, except who picked it up? Barry Gell-Mann, the big Nobel physicist. So, and now we have things that emerge from this. When you ask an economist, what's the worst case scenario? He tells you, I'll die. Okay? No? Is that the worst case scenario for an individual? Okay? No, because think about it. You can die, but there's worse, that your family, friends, and pets die. Okay? That you die and your arch enemy survives. Okay? So there are layers. The tribe dies, the self-defined extended tribe dies, humanity dies, ecosystem dies. Okay? You have a shelf life of, in Cambridge, I think your shelf life is about 115 years. No? That's what okay, because the air is clean and it's a relaxed life. All right? And you have, nice theaters. Okay? So, but then your family, you want them to survive longer. The tribe, you want it to survive longer. The self, humanity, you don't want it to have another only 50 years, okay? And ecosystem forever. There's some risks you can never take because you're going to assume if something's going to live for the next million years or 10,000 years, how many times can we take it over the next 10,000 years? This precludes from some classes of risk. Hence the precautionary principle. Hence my smear campaign on the part of Monsanto. Because I got to have a case because you don't smear campaign. They sent 1,500 letters to NYU, the university, Monsanto. They wouldn't have sent 1,500 letters to university if my argument was weak. You get the point? That there's some classes of risk that are fat-tailed. Why GMOs are fat-tailed, but not conventional agriculture. And you can show the difference between the two. So this puts some structure around the idea of risk. But again, I mean, the person who's a total genius, is him. Or these two guys, who really figured it out because they had the aggressive behavior of true scientists to look back and say from Bernoulli to they all got it wrong. You see? The only guy who got it right is Kelly, using log. You see, log utility or stuff. And Samuelson got it wrong, of course. And he shows you all the textbooks. This is him. And he's visibly now not continuing because he stopped going to the university. But his paper is unnoticed in economics by the economic establishment. Unnoticed, okay? They wrote actually 3 of them, Peters and Gell-Mann, on that difference between time probability and showed a lot of paradoxes disappear. But I'm not using, I'm backing up with their argument. I'm going in a different direction with precautionary. It gives exactly the background for precautionary. A principle that we need. And again, you can't use naive statistic by saying 5 or 6 doctors agree that Relate is completely safe, which is basically, okay, so you can't really say that as people said 80% of scientists agree that, that GMOs are safe. You can't go by that, okay? There's a structure to it. So let me wrap up. I'm finishing. Now there is something, and I have this fellow, I'm so happy he's out of the White House. Of course, the left guy also, but these guys are our enemies, the precautionary principle, because they use naive approaches. If you don't make a distinction, mediocre stand, extremist stand, what do you have to remember here? You have to remember thin tail, fat tail. Different reasoning. If you don't make that distinction, you don't have any point. Secondly, if you don't make distinction, time probability versus ensemble probability, you don't have a point. You see? The time probability, what happens to you over sequence, which is path dependent, and ensemble probability, which is path independent, taken from sample of people around, okay? So that's what we call the ergodicity problem. And they miss on it, and then their job is to nudge us. At some point, they were bothering David Cameron, and remember? He had the nudge group, which horrifies me. So nudging people into rationality, not understanding that it's they who are irrational. You see, they have an incomplete understanding of probability. So let me stop on here. So this is telling me to stop with one final slide, what to do. So this work was up till the black swan, actually, I tell you. I abandoned work on probability after the black swan. Okay, I still publishing papers that were written before. All this work has been up till the black swan. Phase 2 of my life, focusing on heuristics, how to detect things. Okay, that's anti-fragile. So I'm not going to give a second lecture now on anti-fragile and spend the night, but So let me give you the point, really, the trick. The trick is that whatever is fragile, instead of focusing on random events, once you know it's fat tails, you forget about you're just focusing on how things react to random events. And we build heuristic to see how they react. And there's something beautiful we discovered, is that everything fragile has to have a concave exposure. In other words, has to have harm that accelerates with intensity. So for example, our body is fragile. If I jump 10 meters, I'm harmed more than 10 times than if I jump 1 meter. Okay, and that's the property of fragile, and we look at acceleration in the tails. So build some heuristics, including stress testing heuristics, which is published by the IMF, but not applied by them because it's too simple. Okay, so that, I mean, this is why I can't wait to drain the swamp, because in the real world, you want a simple thing that works, not something complicated that impresses a peer review. You want something that impresses reality. You want to impress your accountant, not your peers. But what happens is that the techniques, you cannot survive unless we have clear techniques. And these techniques map to our intuition. So you can measure acceleration. That's the book Anti-Fragile and the associated papers, including the heuristics papers, on how to detect concavity and figure out if you're fragile to tail events, which is much simpler than probability. So thank you for listening to me. I'm honored to be in Cambridge. I'm honored to make my case. Sorry if I'm angry sometimes, but you know what? There's something wrong with the social science establishment, or some parts of social, outside Cambridge, of course. All right? Thanks for listening to me.
So, Nicholas Taleb, thank you very much indeed for your insight into the key importance of a proper understanding of data distributions, risk, and statistics, clearly essential, not just for a few people, but for many in our societies. I wonder how many of you are actually watching 1970s TV repeats, or even seen the last year's film. You'll know about Private Fraser, the undertaker from Barra. "We're doomed," he cries, but Captain Mannering ignores him. Of course, Fraser's right, but pompous Mannering is just too obtuse to realize that. Sometimes just blind belief in the continuity of order has its own reward. You know, everything survives, but of course not always. To go back to the Greeks, I mean, Cassandra was right, but not believed. There were warriors hiding in the horse, and Troy did fall. But to bring this to economics, I recall the Queen's question after the financial crash. Question to the experts: why didn't you predict it? And I guess we've had part of the answer explained to us here tonight. Next week, our journey to the extremes takes us to conspiracy theories and post-truth politics. Professor David Runciman, Head of Politics and International Relations here in Cambridge, will speak to us on dealing with extremism. I hope to see you then. But finally, let us just show Nicholas Taleb our appreciation once again.